You build the robot, upload the code, set it loose, and watch it drive full speed directly into your couch, without even tapping the brakes. It's a frustrating rite of passage for almost anyone using the HC-SR04. This is the universally adopted, ultra-low-cost ultrasonic distance sensor found in nearly every beginner robotics kit. On paper, it boasts some highly attractive numbers. The spec sheet promises a maximum range of 400 centimeters and an incredibly tight 3mm accuracy. Makers overwhelmingly choose this component because it offers an unbeatable, budget-friendly ratio of price to precision. But then, you deploy it. You check your math and verify your microcontroller code is flawless, yet the hardware still behaves erratically. Your project suffers from phantom collisions, or the sensor registers exactly 0 distance when an obstacle is sitting right in front of it. On the left are the theoretical promises of the spec sheet. On the right, a blank slate for the chaotic variables of a real-world deployment. That empty column is actually governed by undocumented environmental edge cases that your code simply cannot fix. These failures are caused by physical environmental factors that cannot be addressed within the microcontroller code. Look at this quadrant chart mapping environmental efficacy. Across the bottom, we have material density, from soft and porous to hard and reflective. Up the side, we have surface angle, from tilted to flat. The top right is your optimal safe zone. High-frequency 40 kHz echolocation thrives here because it bounces cleanly off hard, flat surfaces. But the entire left side of the chart represents the acoustic failure zone. Here, the physical properties of your target object completely destroy the sensor's functionality. When high-frequency sound ripples strike a textured, porous surface, they dissipate into the material. There are no returning waves left behind to bounce back. We are talking about everyday domestic environments, living room couches, carpets, and clothing, or stuffed animals. Hitting these absorbent materials renders the sensor completely blind. As far as your microcontroller knows, the path is wide open. That vaunted 3mm accuracy is highly conditional. It is entirely dependent on the material density of whatever sits in front of it. The sensor achieves its low cost by relying on a strictly directional, paired transmitter and receiver setup. The transmitter fires an 8-cycle burst of sound. To get a reading, those waves must travel a straight line out, hit an object, and travel a direct line back to the echo pin. This diagram shows what happens when that directional sound burst hits a surface tilted at a shallow angle. Like a pool ball bouncing off a cushion, the sound waves deflect away into empty space, missing the receiver entirely. This causes the navigation system to fail. The robot assumes the silence means the path is clear, and it crashes straight into the angled obstacle at full speed. This geometric limitation pops up any time your project approaches a wall diagonally or attempts to navigate irregular, uneven terrain. Perfect geometric alignment, the angle of incidence, is just as critical for success as the actual distance to the object. Then there is the hard physical limit on range. Any object placed beyond roughly 13 feet or 400 centimeters is entirely invisible to this hardware. That 13-foot ceiling is dictated by a strict 38-millisecond timeout limit hard-coded directly into the sensor's firmware. This timeout is necessary. It forces the sensor to stop listening, so your Arduino code doesn't permanently freeze while waiting for an echo that is never coming back. While it saves your code, 13 feet of warning is a dangerously short braking distance for fast-moving vehicles or drones. Even when it works, there's a computational cost. This is the formula required to translate the returning sound pulse into a usable distance metric. Processing this formula requires your microcontroller to constantly dedicate CPU resources to timing a 10-microsecond trigger and listening for the return pulse. This constant polling requirement creates a serious processing bottleneck for complex projects that need to manage multiple sensors or drive motors simultaneously. Ultimately, the HC-SR04 places a strict hardware ceiling on both the physical speed and the computational scale of your project. This scorecard lays out the final evaluation criteria. You have to match this sensor to the deployment environment rather than your budget. It is perfect for builders creating maze-solving robots inside rigid wooden tracks, or for measuring fluid levels perfectly flat inside contained industrial water tanks. But it actively fails for robots expected to navigate cluttered domestic living rooms with carpets and couches, or high-speed outdoor drones. Relying on the HC-SR04 requires managing a very narrow set of physical environmental variables. That alluring $2 price point is only a true bargain if your project's physical environment naturally falls into the sensor's safe zone. If you control the angles and the density of the materials, it performs exceptionally well. But if your environment is chaotic, stop wasting development time trying to fix phantom collisions by endlessly rewriting your math. To achieve professional results on a beginner's budget, you have to deeply understand the physics of your environment before you trust the numbers on a spec sheet.